So take a generic triangle, obtuse or not. Okay, so here's a generic triangle. I'm going to go ahead and consider a point M on the plane of this triangle, which will define three subtriangles. So let's place M in the interior of the triangle. So here are the three subtriangles defined by M. I'm just going to connect M to the three vertices and define these three subtriangles. Now let's compute a Kimberlin center inside of each one of these three subtriangles. For example, the barycenter, x2. Okay, so here's the x2 of this first triangle, the x2 of that one, and the x2 of this third one. And then I can consider the triangle connecting these 3 points, right? And I can visualize this triangle as I slide M around. Okay. Now with the barycenter, something very neat happens, and this is probably easy to prove, and that is that the sides of the so this particular triangle here is homothetic to the external one, and as I slide M around, this guy is just translating, and the ratio of homothency is not changing. Okay. Now how do I know the ratio of homothency is not changing? I'm reporting the area of this barycenter triangle and the area of the original triangle, and I can see here that the ratio of those areas here reported as 0.111 is not changing as I slide M around. Now this is not very surprising. Okay, now what happens, for example, if instead of the triangle of barycenters, I decide to look at the triangle of incenters? So here it is. Here's a triangle of incenters. Let's rotate this a bit. So here's the three incenters. Let's place M inside of the triangle so we can better visualize the three incenters. So this is the first incenter, the second incenter, the third incenter. What's happening to the length and area of this dashed red incenter triangle as I move M around? Okay, so nothing is staying constant. So nothing interesting here for the incenter. How about the triangle formed by the circumcenters? Here they are. Here are the three circumcenters. Let's scale this out so we can see them a little bit. So here's my triangle. It happens that these three subtriangles are obtuse, so the three circumcenters are exterior to each one of the triangles. But the issue here is that as I slide M around, and I'm just looking at the length of this triangle of the circumcenters and the area, as I slide M around, they're not staying constant, so there's nothing interesting. So the really interesting result happens with the triangle formed by the orthocenters. So here are the, let's make this guy sort of less eccentric so we can see the orthocenters sort of here on the screen. Let's choose a good triangle. Maybe I'm going to slide this down a bit. I'm going to slide this to the right a bit, and I'm going to scale this up. So here's a triangle. Here's a triangle formed by, so here's M. Here are my three subtriangles. And here are each of the orthocenters corresponding to each individual subtriangle. Now, a miracle happens here. The area of this triangle, this dashed red triangle, is dynamically equal to the area of its parent blue triangle over all possible choices of M. So I'm going to slide M around. Okay. It doesn't matter where M is. What I want you guys to take a look at is the reported area of this dashed red orthocenter subtriangle being identical to the area of its parent subtriangle. So the ratio of those areas is equal to 1, and of course the product is going to be the square of the original area. But this remains constant, so let's go ahead and take this system up to the top so we can actually see what's going on here. So this area here of the triangle formed by the orthocenters is actually independent of the position of M, and it's equal to the area of the parent triangle. Now, because this is triangle geometry, I believe this is probably provable either with synthetic or analytic geometry, but I thought this was a pretty neat phenomenon. I don't know if it's known, it's probably a classical phenomenon, but I would invite any of you guys to offer a proof to this. Now, does this happen to the Euler, the triangle formed by x5, the centers of the 9-point circles of each one of these triangles? Let's move M around. No. Does this happen to the triangle sine medians? Also no. Nothing is constant here. No ratios are constant. How about x7, the Jargon point? Jargon point also doesn't preserve anything. How about the Nagel point? Also doesn't preserve anything. How about the triangle formed by the Mittelpunkt, or the Mittelpunkten um, of the three subtriangles? Nothing special here. We can go to the speaker center or speaker center. Also nothing special. We can go to Feuerbach's point to see if anything interesting happens here. Nothing happens. Okay, so it looks like the orthocenter is very special. Let's go back to the orthocenter. And of course we can go down Kimberling's list and we can test if there's any other point in Kimberling's list. It has this property. I haven't done this yet, but I just wanted to report in this particular video what was going on with the orthocenter. So let's actually just recap. You take a triangle, a blue triangle, and you define a point M on its plane, anywhere interior or exterior to the original triangle. And that's going to define three triangles. Here's the first one. So for this first triangle, compute its orthocenter, it's over here. Then for the second triangle, this other one here, compute its orthocenter. Now this one is acute, so its orthocenter is over here. And then for the third one, this third triangle is actually exterior. Compute its orthocenter, it's over here. Now the result is that the area of this triangle defined by the three orthocenters is invariant and equal to the area of the parent triangle over all choices of M. So as I move M around, right now I'm sliding M horizontally, I could slide M around vertically, and that does not alter the area of the dash red triangle. Okay guys, so see you in the next video. Thanks for your time.